right now, it will record everything that's projected on the screen with what I'm saying in sync, and then after class is over with, then I upload that file to YouTube. Okay, it takes a couple hours to upload to YouTube, but when it does, and I have a chance, then I move it to the YouTube playlist for this course. Okay, so let me pick up from there and go. And for those of you who were here last time, this will be some new information for you too. Finally, over the weekend, I started it Friday and had really bad luck Friday getting PowerPoint to load files, but I finally got them done over the weekend at home, and I think the problem had been the bad signal that I have at my office on the Birmingham campus. But whatever the problem was, it did work. So right now, I have uploaded for this class your syllabus, and that's out there. Are you familiar with Blackboard? Okay. In Blackboard, you know, there's, and when you go to the home page for this class, there is a, on the left-hand column, there's a bunch of blue tabs, or at least they're blue in the instruction module. They're grouped in groups of 7, 8, 9, something like that. Okay, in that first group, about the middle, it says syllabus and book information. Okay, in that one, I place the syllabus. Okay, so you can go back, read, see the syllabus, okay, that type of thing. The tab just below that says instructor and some other kind of information. I can't remember exactly what that is. But anyway, that's where I put my locator card. My locator card shows when I'm on campus, off campus, in class, out of class, lunch, that kind of stuff. And when you look at it, you'll see there's only very few spots where I have any office hours. But you're welcome to come see me during the office hours. Okay. The office hours are also listed in the syllabus. Okay. They're listed more graphically in the locator card. Then in the next group of blue tabs is one that says handouts, PPTs, and more. PPTs are PowerPoints. Now the only handout, I guess, that you would say I have in there is your research paper instructions. Okay? And they are in there. You can read those and find out what's required in the research paper. Then the PowerPoints are there. Every PowerPoint we could possibly have. We actually started this, one of the students who's not here right now but requested we go over 5.2. So we went over 5.2, so that PowerPoint show is there. Then we went to 7.1, and that's where we are now. So beginning at 7.1, we do all the rest of the possible sections that we'll conceivably do in this course, okay? More than we will do, but, you know, every one that we might do, okay? I may do just PowerPoint shows on some of them, but we won't do all of them in depth. So those are there. Then after them, I believe, somewhere after them, is one that says MTH126 YouTube videos. That's the one that has the videos that we've already done. But Mondays and Wednesdays videos are there. But that's not all that's there. You'll also find, if you go to it, that videos from last summer when I taught this course are also there. Okay? They're at the top, and then the two that we just did are at the very bottom. The one we did Monday says Math 126 syllabus, and the one below that says Math 126 5.2, I believe, or something like that. But those at the bottom are the most recent ones. The ones at the top are the older ones. Now, you may say, why are the older ones still there? Well, every now and then, something goes wrong, okay, believe it or not. My computer doesn't work properly. The system goes down. The server goes down. The supercomputer in Huntsville goes down. It has also happened that somebody forgot to pay the bill to Screencast-O-Matic, and they cut us off. Okay, so whatever the reason, every now and then the system doesn't work. Okay, and so I'll leave all of them there, so in case one day I just have to teach from the board, you'll still have videos that cover maybe not exactly what we covered that day, and not starting and stopping in the right place, but you have most of the material covered. Okay, so let's go back. The first one, next to the last one that you see down here, the syllabus. Not only do you see the syllabus up there in that blue tab that says syllabus and I guess book information is what is there. Okay, that's in static form. When you go to the one in the YouTube videos down here, handouts, PowerPoints, and more, do the YouTube videos near the bottom, then you'll hear me talk about the syllabus. Now, I'm referring to the one we did in the summer, but I'll tell you what the corrections are. Not many, it's just little things like office hours and things like that. Okay, and then I'll talk about research paper. So again, you can see that at the beginning of this group handouts, but you can also hear me talk about it in the YouTube videos. Also, my locator card, I talk about it, is located up here in static form. Down here is in more dynamic form. You hear me talk about it. Then we talked about safety, and those are important things to know and keep in mind. Now, a lot of that is arm waving. There's not any videos for it, so you just hear me talk. So you sort of have to imagine what I'm talking about. But if you have any questions, please let me know. Okay, and then once we got going, I use the PowerPoints. So you had them up here in static form, and the YouTube videos there, and I write on them, I talk about them, all sorts of stuff like that, which is what we're going to start right now. Any questions? Okay. Okay. And welcome to the class. Okay. We got started on 7.1 last time. We didn't quite get a full page done, but we're on the bottom of page 444. And by the way, I can't remember if any of this class specifically said they wanted or needed access to a, what do they call it? An access number or something like that in order for you to have access to either your, whatever you call it, ebook or WebAssign or anything like that. Did any of you particularly need that? You do, okay. I'm going to try to get in touch with Cengage today and get them to send me the codes. The trouble is, this is a very busy time for them at the first of the term, and sometimes they're really slow getting me the codes. But I will get in touch with them today if I can reach them. I had trouble getting in touch with them on Friday, but that was for a different issue, and it was a pain in the neck, but we finally got that issue straight, but I forgot to ask them about the YouTube. Well, I was talking to the wrong division of Cengage. I'll have to get to the right people. Okay. I'll try to get that done today if I can. But that doesn't mean the code will be available yet, but it will be. As soon as they can get me the code, I'll give it to you. Okay, so if you don't have a book and you want to look on with someone who does, there's a few of them sitting around here, or you can just follow where we are. We're near the bottom of page 444. We were talking about, let's just go back and see, how you integrate between two curves, okay? And the area between two curves, okay? And between 2 points between the two curves. If this is the upper curve, we call that F in this case. The lower curve is this one represented by the function g that represents the function g. Then the area between these two curves, if you split, and we're only measuring from A to B, and the important thing here is that F always be greater than or equal to G everywhere between A and B. Obviously out here, if you're out here, it wouldn't fit that bill because here F is less than G. But as long as you're within B, actually you could go a little bit further, where they're equal, that would be fine. And somewhere back here, they would become equal again, it looks like. That would be fine, but they did A to B, so you're completely in the range where, or in the domain where F is greater than G. Then you can do your little Riemann sums like triangle. The length of, rectangle, the length of this rectangle is f minus g, that's the length of it, and then the width of it is delta x. So the area is going to be the sum of all those, or approximated by the sum of all those, as x goes from A to B. So that's what we're dealing with here. Now they're going to introduce sort of a new term, and this is going to be delta A, which means that little area increment. And that would be f minus g dx. Okay, and that's where we began here. That area of that little rectangle, that representative rectangle, is delta A sub I, that's the ith one, somewhere between A and B, is the height times the width. The height is f of x of I minus g of x of I, and the width is delta x. By adding all those areas of those n rectangles, n is the number of divisions you have there, and taking the limit as this is called the maximum partition. That symbol is del. There's a name for that. I can't think what to call it now. But anyway, the maximum partition is approaching 0. That means n is approaching infinity because you're getting more and more and more, so your maximum partition is approaching 0 as n goes to infinity. Then the limit as n goes to infinity of this summation of f of x of I minus g of x of I delta x moves to, as n approaches infinity, that moves to the integral, which is just what we saw in Riemann sums and stuff. Because f and I are continuous on A to B, f minus g is also continuous on A to B, as long as you're within those. And the limit does exist, so the area is given by the region. This is the area, approximate area. Limit as that goes to infinity, the summation becomes an integral sign, and you're going from A to B, limits on x, and what was your delta x is now your dx, and you have f of x minus g of x dx. So that's your area between two curves, f and g, as long as everywhere between the limits here, A to B, that's on x, f is greater than or equal to g. Okay. Here's how they summarize that. If f and g are both continuous functions on that interval A to B, those are values of x on A to B, and g of x is always less than or equal to f of x for every x on A to B, then the area of the region bounded by the graphs of f of x, g of x, and the vertical lines x equal a and x equal b is given by this integral, which we just saw, integral from A to B, f of x minus g of x. That's the height of that rectangle, the length of the rectangle, times dx, which is the width of the rectangle. Integrate that from A to B. Definite integral. Any questions? All right. And this figure, 7.1, which is very similar to what we saw before, almost identical, maybe identical. The graphs of f and g are shown on the above, shown to be above the x-axis. F and g are shown up here. Now, back when we were doing the area under a curve, it was absolutely necessary for the f or g to be positive. Now that we're doing the region between the two curves, it's not, because f minus g is always a positive height, okay? The dx is your width, okay? If you had this curve and you scooted it down here, so g was sometimes negative, could have been negative, you're still measuring that difference here. That's a positive value. So that's no longer necessary. The same integrand, f minus g, can be used as long as f and g are continuous. One thing, g of x is always less than x on this interval A to B, for all x in the interval A to B. So the part of this could be below the g. Both of them can be below. It doesn't matter because f minus g is positive F minus G is positive as long as F is greater than G. F minus G is going to be positive, so they can both be, one or the other or both can be below, can be negative. That wasn't true when we were just measuring the integral of the area under a curve. We had to have the entire curve to be above the x-axis. Above the x-axis. Okay. So this height is positive no matter where that graph is. Okay. Any questions? And here's Josh.
Dawson showed him his way to. We both are leaving the same class.
Oh, I see. Okay. And you even brought in Ryan? Ryan's here. Okay. All right. And I know I saw Josh. Here you are. Okay. And maybe Dawson will show up. Okay. Now, Ryan. Okay. Okay. And did you get your schedule changed? But you left it the way it is and you're okay with it? Okay. All right. Any questions on this? That is top of page 445. Think we're ready? Oops, no. Representative rectangles are used throughout this chapter in various applications of integration. A vertical rectangle, where the width is delta x, implies integration with respect to x. Whereas a horizontal rectangle, that's width is delta y, then you imply that you're integrating with respect to y. The integrals work just as well. You usually have to have your function over here as a function of y, and the function over here as a function of y in order for that to work, for your variable to be dy. So here's example 1 for 7.1. Find the area of the region bounded by the graphs of y is equal to x squared plus 2 and y is equal to negative x, x equal 0 and x equal 1. Okay. Now, generally, not a bad idea to draw the graph. Part I don't particularly care for too much. And if you use what you know about graphing, you can make this happen a little bit more easily. Let me get my pen set up. Black. Okay.
This is 7. What?
This is 7.1, page 445, example 1, near the bottom of page, bottom half of page 445. Okay? Now, we're going to be, x's are always going to be positive, so we can put the y-axis here. And since x's are positive, y are going to be negative, so let's put the x-axis there. And x is going to start at 0, so y is going to start here at 2. Okay? And okay. This part is going to be a half of a parabola. And when, oh, he decided to show today. All right. Dawson's here. Boy, what class are y'all coming from? Birmingham campus? Huh?
Yes, sir.
Yeah. Oh, wow, okay. Understood. That's a haul, and especially weather like this, not a fast haul either. What class is it?
Swimming.
Say again?
Swimming.
Oh, wow. Oh, y'all could have just kept on swimming over here, right? Never mind. Okay. Okay. Let's see what happens when y is equal to 0. When y is equal to 0, then x squared is equal to negative 2, which doesn't make any sense, does it? Well, that is because the graph is going up here. So that's absolutely true, okay? When x is equal to 1, this is equal to 3, okay? I didn't draw my curve too, it's even worse. Something like, there it is, okay. So there is your first function. Sort of. If I can get my eraser to show up. Okay. All right. There's the first function. Here's the second function. Y is equal to negative x. So it starts at 0 and goes to negative 1. Okay. So we're doing in between these values. Okay. And we're doing the area bounded by the graphs between those two graphs. Y is equal to x squared plus 2, and y is equal to negative x. Okay? Your little rectangles would be something like this, and it's always y1 minus, or however you want to do it, y2 minus y1. That's going to be the length of the rectangle. So that would be the integral, the area that we're looking for, would be the integral between x equals 0 and x equals 1. Yes, sir. Okay, wait just a second. Okay. The area between these two curves and between x equals 0 and x equals 1 would be the first y here, that would be x squared plus 2 minus a minus x, which would be plus x. That's your difference between the two functions, dx, as you go from x equals 0 to x equals 1. Does everybody see how that's what you get when you're integrating these? Now you can integrate, yes.
How do you get the 1 and 0?
It tells you here, x equals 0 to x equals 1. Yeah, yeah.
Where did you get the x at the end?
Where do I get what? Okay. Okay. I probably should have written this down. Area is equal to, I changed this to y2 minus y1, and that would be the integral from, let's change this to a and that to b. Integral from a to b, that's where the 0 and 1 comes from, y2 minus y1 times dx. Okay? And y as a function of x would then be the integral x equal a would be 0, x equal b would be 1, and the y2 would be x squared plus 2 from this one, minus x dx. And that's what produced that. Make better sense? Sorry. Sort of skipped a few too many steps. Now, if anyone is particularly anal retentive and wants to have these things in descending power, you can do that. But you can integrate it just like it is there, can't you? Please say yes or not. So what is the integral of that? Antiderivative of x squared would be x cubed over 3 plus antiderivative of 2 would be 2x plus x squared over 2, evaluated between 0 and 1. Okay? I'll do the 0 part, y'all do the 1 part. What would that give you? 1/3 plus 2 plus 1/2. I'll do the 0 part, 0. Okay, done. You don't have to worry with that one. Okay? And this would be 1/3 plus 1/2 is? Here's Jemiah. Ding, 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 ding. Perfect attendance today. Way to go, team. All right. We're now up to 1, 2, 3, 4, 5, 6, 7, 8, 9 students. 3, 6, 9. Excellent. And to think at one time I was afraid they were going to cancel the class. In fact, I think they would have, except I was the instructor and they knew I would pitch too big a fit if they did it. So glad y'all are here. Okay. What's 1/3 plus 1/2?
5/6.
5/6. 2 and 5/6. Or if you want to write it as an improper fraction, that would be 17.6. Let's see what the book did. Oh my goodness, they did 17.6. Way to go. Any questions on that? All right. If not, here's how, all right, to erase. Okay, here's how they approached it. They drew the graphs, okay? They drew more of the graph than I did. This is x squared plus 2. That's your polynomial function x squared elevated 2, vertical shift is 2, okay? And your minus the identity function. Identity function would be like this, like that. And we're evaluating only between 0 and 1, so that's all I drew, but they drew a little bit more. Here is your representative rectangle, f of x minus g of x, once you rename that. The problem didn't give you that, but they said, let's name them that way. And you notice here g of x is always less than or equal to f of x in that range. In fact, it's always going to be. Because this is going to keep going like this, and that's going to go up more sharply. They will never will that do. So this would be good for from minus infinity to positive infinity. This would be still the way to go. Okay? But certainly for all the x's at 0 to 1, it's shown here. So that's your representative rectangle. The difference between those is the f minus g. G is a minus x, so that's f of x, which is x squared plus 1, minus a minus is plus x. That's your function. So the area of the representative rectangle, your delta A would be your f minus g times your delta x. That would be x squared minus 2 minus a minus x, delta x. Writing that as taking a limit, so to speak. As the delta x becomes your dx, then you're going from a to b, in our case 0 to 1, of the difference between f and g, which we know to be x squared plus 2 plus x. And, okay, filling in just like we did, a is equal to 0, b is equal to 1. There's the difference between the two functions. And they skipped some pertinent steps, and they rearranged the order. Perfectly fine, it doesn't matter, but we see we got x squared, the antiderivative of x squared is x cubed over 3, so this becomes a plus x, they move that here, x squared over 2, antiderivative of that is 2x, evaluate that from 0 to 1, and sure enough you get 1/3 plus 1/2 plus 2, because all the zeros go to 0, and you get 17.6, or 2 and 5/6, or whatever. Now, for those who did come in a little late, let me go back and explain a few things that I said before. Right now, I hope I have all of your Blackboard set up properly. Your syllabus is out there with corrections made to it. Your locator card my locator card is out there. The research paper instructions are out there. All the PowerPoints are out there. The link to the YouTube videos out there. And the one thing I forgot to say, I also put, I think maybe about 6 files or links that either students have found or that I found out about that you might or might not find useful. They're there too. And you can just click on those links and they take you to sites. Now let me say something about those. Those that are associated with this text, they're still in the previous edition. I keep checking and they haven't updated their edition. I don't know why. Maybe they have. Maybe you can find those files with updated editions. If so, get me the information. I'll try to get those updated as well. I have precious little time to do this kind of stuff, so I usually don't take too much time sorting through what they've not updated. So anyway, it's there. All that's out there. So you can go back on the YouTube videos and review anything we've done. So any questions on this before we move on? That's example 1. All right, now we're going to talk about the area of a region between intersecting curves. Now, intersecting curves, we saw places where it looked like these curves are going to intersect. Example 1, the graphs of F and G do not intersect anywhere, and I pointed that out to you. G is always less than F, okay? The values of A and B are given explicitly. A more common problem involves the area of a region bounded by two intersecting graphs where the values of A and B must be calculated. So that's what we're going to do in example 2. Find the area of the region bounded by the graphs of f of x is equal to 2 minus x squared and g of x is equal to x. Now, it's not completely obvious who's on top, is it? Unless you actually do draw the graph, or at least representations of the graph. All right? And since we have no clue of what we're dealing with here, let's just draw the graph kind of in the middle of the page. See what we got. Let's get f of x graphed. What can you tell me about f of x? It's a parabola, that's one thing. It's opening downward. So there's a really good shot that this is going to be the one on top. But we don't know that. Let's proceed. Let's give me a few points that f of x would have on it. What's a real good xy point to choose?
Y equals 2, right?
Say again?
Y equals 2.
When y is equal to 2, that's f of x is 2 when? X equals 0. So here's 1, 2. Okay? There's that. Now, I don't usually do it this way, but give me a color for G. I want to do it in a different color. Pick a color, any color, not black. Red. Okay. Bright fire engine red. When G is equal to, when X is equal to 0, G is also 0. So it looks like to me that G is going to be the lower function. Okay? Let's go back to F then. I just want to do that to show. Well, let me go back. G is going to be so easy to graph. Let's go on and do graph. Okay? How will G go? It's the identity function. Okay? Whoops. Doesn't have a curve in it there. Something like that. Okay? Now let's do F. We know it starts at 2, 0. I'm sorry, 0, 2. All right, give me another point. Give me an x. Football. 1. When x equals 1, what do you have for the y value, the f value? It's also 1. Well, that's on the identity function. That's right there. 1, 1. So we found one point of intersection. Where's another? I wouldn't go any further to the right because after that, you know that this is going downward, so then they're going to cross. That's your point of intersection. Let's go to the left. Give me an x. Negative 1. What would your y be? It would be negative 1. No, it would be 1, wouldn't it? It's a parabola, right? Negative 1, 1. Okay? Give me another x. Negative 2. Okay? Negative 2 squared is? 4. 2 minus... Okay, let me get... 2 minus 4 is negative 2. So that would be down here somewhere. I think we found another point of intersection, didn't we? Right? Negative 2, negative 2. All right? So this is what the function looks like. Now that was done graphically. Not my favorite. But what can you tell me about these 2 points of intersection? Because that's what we're looking for, is the points of intersection where this terminates. See, after this, F is less than G, you can't talk about F minus G. Less than this, F is less than G, you can't talk about F minus G because now they're negative values. So you can talk about F minus G in this region alone. What else is true about these 2 points of intersection? Isn't F equal to G there and there? So you could have found these by doing this. Setting F equal G, which is 2 minus x squared, is equal to x. Solve that equation. How can you do that?
Put it all on one side.
And which side would you like it on?
Right.
I would, okay. So let's add x squared to both sides and also subtract 2 from both sides. I'll do it in strange order, but we'll do it. So this side becomes 0. This becomes x squared plus x minus 2. Now what do we do? Unfold it, okay. Factor it, and what would that give you? X plus 2 times x minus 1 is equal to 0. And what does that give you? X equal negative 2 or x equal 1. There we have negative 2. X equal negative 2, and here we have x equal 1. Sure enough, we found it that way. Now what we couldn't find is which one's on top. But just plotting 1 point gave that to us. X equals 0, F was 2, G was 0. So you know F's on top everywhere between those 2 points, because that's the only place. Both of these are continuous functions, so we didn't actually have to graph it. But I thought maybe this time it wouldn't hurt to do so. And here is your representative rectangle. Of course, F is on top. So what would be the area bounded by the graphs of those 2 functions? Help me. The integral from negative 2 to 1. Perfect.
y2 minus y1 or y1 minus y2?
You tell me. F minus G. Perfect. And what would that be then?
2 minus x.
Wait, I've still got to get my pen back. Second?
2 minus x squared.
2 minus x squared minus x. dx. Perfect. And that area would be? Second?
So how do you know which order to go? And he said because the parabola was on top.
Say that one more
I
time.
asked him how do you know which order to go as far as y1 and y2.
Right.
He said the parabola was on top.
Yeah. The F is on top, the G, the red is on bottom. Between these 2 points. After those 2 points, not true anymore. Okay? This continues going down here, this is down here. After those, outside those 2 points, red's on top and black's on bottom. Okay? But between these 2, F is greater. I don't think I had to do anything there, so, okay. So let's proceed with the integration. What does that give you? Help me, somebody. 2x
minus x cubed over
3 cubed over 3
minus x squared over
minus x squared over 2 from negative 2 to 1. Okay? Uh-oh, no zeros on this one. I'm not going to volunteer anything here. Okay? So you tell me what we do. I would almost, yeah, plug in the positive 1, and what do you get? 2 minus 1/3 minus 1/2. Plug in the negative 2, but we're subtracting then. And what would that give you? Minus a minus 4, right? Because you're subtracting the lower one, right? That would be plus 4, right?
Plus 8 over 3.
Which one? What sign?
Plus 8 over 3.
Plus 8 over 3. Okay, I'll buy that because it's minus. I don't think I buy that. Yeah, watch those signs. The whole purpose for signs is to reach out there and trip you. Okay? Okay, what we have here is very to communicate. No. What we have here is plug in minus 2 here. Minus 2 cubed is minus 8. Minus times minus would be positive 8/3, but we're subtracting, so it's minus 8/3. Remember? You subtract the lower one. Here you got away with a plus because 2 times minus 2 was minus 4, but you're subtracting that, that's a plus 4. Here you have a minus, and a minus. So that's 3 minuses make it a minus. Okay, next. Say again? Okay, how did you get it?
It's 2 squared, right?
Yeah.
So that's a positive.
Right.
Divided by 2. We give you a positive 2 plus negative. Plus 2.
Plus 2. Okay, I thought you were going to get there, but you kept talking yourself out of it. When you plug in the minus 2 here, that becomes plus 4 up here, and that would be minus 4 over 2 would be a minus 2, but you're subtracting it, and that makes it a plus 2, because it's the lower limit. Okay? So, let's add all the whole numbers up, and what do you get? Say again? 8, okay? And then let's add your 2 negative thirds, and what do you get? Which is 3, and you finally have a minus 1/2 left over. So the 8 minus 3 is 5 minus 1/2, 4 1/2, which would be how many halves? 2 times 4 is 9 halves. Is that what you said? Please say yes. Okay. 9 halves. All right. There we have, yeah. 9 halves. I was looking on the wrong page. I went, how did they get that? All right. Everybody see that? Watch those signs. The whole purpose of them is to trip you up and make you fall. And it almost did it. Does this make sense? Let's see how they did it. Can I erase? Okay. In figure 7.6, this is it. Notice that the graphs of F and G have 2 points of intersection. They'd appear to be at minus 2, and at 1, 1. Okay. Find the coordinates of those 2 points. Set F and G equal to each other, which you get minus x squared. They put it on the other side. Minus x squared minus x plus 2 equals 0. Boy, did they do it strangely. Okay, I would multiply everything by minus 1 and make it, but that's me. So this gives you x equal either minus 2 or x equal a positive 1. Okay, that's exactly what we found. So those are the limits. So a is minus 2, b is 1. And because g of x is always left in x between those points, negative 2 and 1, the representative rectangle delta A, area of that representative rectangle would be f minus g times your delta x. That would be 2 minus x squared minus x times delta x. So the area would be the integral from minus 2 to 1 of 2 minus x squared minus x dx. And that would be, again, they rearrange and do all that without showing you they did it. They move this up front, minus x squared. Move this next, minus x, plus 2 here. Then they integrated. And that's exactly what we got, maybe not in the same order. Evaluated from minus 2 to 1. And then without showing you how they got it, they just said 9.5 is the answer. Wasn't that fun? Okay. Please be careful when you're doing your integration. Remember, it's the upper one evaluated at the upper value minus evaluated at the lower value. Watch your signs. Okay. Make sense? Okay. Now, they love this next one. Integration is the accumulation process, but that's a couple of pages off. They're skipping examples 3, 4, and 5. So let's us go back and pick up 3, 4, and 5. Okay, I'll try it right here. The sine and the cosine curves intersect infinitely many times, bounding regions of equal areas, as shown in the figure here. Well, unfortunately, they want me to draw it too, because they didn't show this one. Why couldn't they have shown this one? Okay. All right. My x-axis shouldn't be dipping like that, but we're stuck with it. All right, let's graph first the sine function. Where does sine begin? X equals 0, 0, 0. Is that what you said? Yeah. And I've ticked off a few points here, and I want these to be pi halves. That's a 2 pi. I don't know where that came from. Okay. Okay. We don't need that many. So for the sine function, x starts at 0 and does where? This is not drawn to scale. I admit that. It goes up to 1 at pi halves, down to 0 at pi, negative 1 at 3 halves pi, 0, 1, 0, negative 1. Okay, we got the general plan there. Okay? I'll even try to draw the curve. Okay, something like that. For some reason my pen picked up. I didn't quite hit my points well, but something like that. What does cosine do on the other hand? What color you want cosine to be? Say again?
Yellow.
Yellow, going to be hard to see, but we can do it.
We want cosine to be at 1.
Okay, at 0 it'll be 1. Pi halves it'll be 0. It'll be what? Negative 1. 0. 1. 0. Negative 1. 0. Okay? So the cosine function does something like this. I told you it'd be hard to see. But let's find any old area where between two intersection points. Here's one such area. Can I do it in yellow? Here's another one. I'm going to do this and give me another color.
Green.
Green. Okay, here's this one in green. How about another color? Blue. Okay, this one in blue. And what do you notice about those? Even in my ugly drawing, they sure seem to be the same areas, don't they? So, pick any 2 points of intersection, and then what's the important part? Good old competition. See who's on top, okay, right? Okay. So if you do the first yellow here, who's on top? Sine. Well, we got to figure out what points they have in common, because that's where we have to begin and end our area. Any ideas? It can look like something, but I wouldn't trust that until I tried it. Okay, and this is the black here is the sine function. And the yellow here is the cosine function. Okay? Sine's on top, so let's draw us a representative rectangle. I'll do those in blue since we're... Here's your representative rectangle. One of those rectangles there, it doesn't matter which one. So what would be your area? Well, we first have to say, determine what are our boundaries. Sure look like a certain value to me, but I can't do it until we do. It looks like pi fourths. Let's verify that. We're looking for places where sine x is equal to cosine x, right? Okay. Ooh. And I think we know that too, don't we? Pi fourths, exactly. Sine of pi fourths is square root of 2 over 2 when x equal pi fourths. And cosine is equal to square root of 2 over 2. Okay, is that also true? What is your guess at this value?
5 pi fourths.
5 pi fourths. And what is sine of 5 pi fourths? Really? It's negative square root of 2 over 2. And what is the cosine of 5 pi fourths? It's also negative square root of 2 over 2. So yes, what looked to be true is going to be true. So those are going to be the limits of our integration by x. What will be our integral? The area between these curves is going to be between pi fourths, I can't get the pi to right, okay, it's pretty ugly, and 5 pi fourths of sine x minus cosine x dx. Can we do that integration? Antiderivative is what? Negative cosine x minus sine x, evaluated between pi fourths and 5 pi fourths. Okay? Well, let's plug and chug then. We already had determined what cosine of pi fourths was, and what was that again? Say again? Negative, but we got a negative in front of it, so that gives us a square root of 2 over 2. Okay? Maybe you were answering that question. My screen is falling on me, so it's hard to write well, period, but it's hard to write. Okay, so that's root 2 over 2. minus a sine of 5 pi fourths over 4. And what was sine of 5 pi fourths over 4? 5 pi over 4. I can't talk. That was also that, but then you got to minus that, so that's going to be a plus root 2 over 2. Okay? And then when we subtract the lower one, what is the cosine of pi fourths? Did it right there. Okay, this is positive, but you have a negative sign in front of it, but in its lower limit, so that's a negative of negative, which is another plus root 2 over 2. But then when you do the sign, you got a minus, another plus root 2, I think. Let me look at that and think a moment. Yeah. So what does that add up to? Four root 2 over 2, which is 2 root 2. Okay, that's what I think it is. And look at that, and the answer, they got the same thing. What's that? This rectangle? Okay, it's just the sine minus cosine. Sine minus cosine. That's what you're integrating. Where was that? Right there. Sine minus cosine. That's your height of the rectangle times your dx. And then when you integrate the sine, you get a minus cosine. Integrate a minus cosine, you get a minus sine. That was step to see what goes in the radicand, and then the next step is what you take the derivative, antiderivative. Okay? Got it? Any questions? Please ask if there are questions. Don't let me snow you with something. Please ask if there are questions. Okay. All right. If none, can we move on to example 4? Now, about example 4, I'm going to use the same slide because it's not given in the slide set, so we're going to work it out here. But if you'll notice in example 4 in your text, if you've got a text, it says see larsoncalculus.com for an interactive version of this type of an example. So this one you can go to that free website. You don't need, and for those people who weren't here to hear it, I'll go on and say this again. This book, I really don't care for Cengage. That's the publisher. But Larson is the best author, in my mind, that I found for, I use them for pre-calculus, algebra and trig, calculus 1, 2, and 3. I even use them for linear algebra. Here's why. He has 3 absolutely free websites. The first one is larsoncalculus.com. Now this is for the calculus text. Okay? Interactive examples, that's what I just mentioned. Videos, 3-dimensional graphs. I don't like to draw videos with Bruce Edwards, who's the second author, and editable spreadsheet. That doesn't mean you can eat them. It means you can edit them. Okay? That's all under larsoncalculus.com. He also, when I give you homework exercises, calcchat.com has worked out solutions for the odd number exercises, which is exactly the exercise that I give you. We'll talk about that when I make some assignments. And then there's also calcview.com. Certain of those odd numbers, not all of them, just a few every now and then, they'll actually give even more detail, interactive videos that help you see how they came up with a solution. Not just a step by step, but you actually see them do it and you can interact with them. So this is Larson Calculus example 4. Even though it's not in the PowerPoint, it will be at larsoncalculus.com. Okay, so let's do example 4. Find the area of the region between the graphs of f of x, which is 3x cubed minus x squared minus 10x, and g of x, which is minus x squared plus 2x. Okay. Now, if you're really big on graphing, we're probably going to have to graph it anyway. But let's see what we can do if we just do it algebraically. Okay? Now, how would you find your points of intersection? How did we do it before? Set them equal to each other. So let's first do f of x, which is 3x cubed minus x squared minus 10x, make sure I copied that right, I think I did, is equal to g of x, which is minus x squared plus 2x. Okay, what do we do with those? You help me. Don't make me do it. Okay, how do we do that?
Add x squared to both sides.
I think I'll do that, and what happens? They both disappear. And then, subtract 2x from both sides, and that gives us 3x squared cubed, 3x cubed, minus 12x equals 0. And what can you do with that? Factor out of 3x, and what does that leave you with on the first term? X squared minus minus 4. Okay. Are you through factoring? No. What else can you do? 3x, that can't be factored anymore.
X plus 2, x minus 2.
Okay. That's equal to 0. And what does that imply? Anybody? X equals 0 is a 0. X equal negative 2 is a 0. And x equal 2 is a 0. We have 3 points of intersection, don't we? Okay? Now, here's what I suggest. This is just my little way to make it, in my mind, a little bit easier. Let's pick a point between x equals 0 and x equals minus 2. What's an easy one? Negative 1. So let's plug in a minus 1 here. F of minus 1 would then be what? Negative 3 minus 1 plus 10. Perfect. And what does that come out being? 6. Okay. Let's pick a point between 0 and plus 2. Oh, wait. We got to do G2. So G of minus 1 is negative 1, which is negative 3. So who's on top? F is on top on the left-hand side of 0. Does everybody agree? Okay? So F is on top. This is on top. I'm going to put greater between minus 2 and 0. Okay? Now let's do the same thing. Let's pick a point between 0 and 2, what could that be? 1. F of 1 would be pretty easy. 3 minus 1 minus 10, which would be -8. Okay? Let's do G of 1, and what would it be? -1 plus 2, which is 1. Who's on top there? G. So G is on top between 0 and 2. Okay. Makes sense? F is on top between -2 and 0, and G's on top between 0 and 2. Okay? That's my way of keeping from having to draw a graph. Okay? I probably shouldn't avoid graphs at that kind of detail, but I kind of don't like drawing graphs. Okay? Not too much anyway. Y'all probably love to draw graphs. And you got graphing calculators, you can show it, okay? Whatever. I just don't have one up here, so I just assume not. Okay? So, what we have then, what our question was, find the area of the region between the two graphs. So the area would be what? The integral between -2 and 0. Okay, let's see. I haven't pulled up my watch yet. We have been going for about an hour and 20 minutes. Y'all want to take, this is really close to halftime. Want to take a break? Well, we just had one person take a break. So you want to take a break? Please try to keep it less than 5 minutes. So, am I right? Yeah, I think I am. Okay. What's that? I can't hear. Yeah, 11:40, and that's going to be about an hour and 20 minutes away, right?
No.
Oh, wait.
It's 20 minutes.
Oh, only 20 minutes left. You want to just keep going? Y'all don't want to go another hour and 20 minutes just for fun today? I mean, it's Tara's first day here. Didn't you want to give her an extra time? Oh, come on. Y'all are just spoiled sports. Okay, you just want to keep trucking?
Yes.
Okay, keep trucking. Yes.
-2 to 0.
I'm sorry?
-2 to 0.
From -2 to 0, yeah.
Why not -2 to 2?
Okay, because we found out that F was on top between these 2 points, but G's on top between those 2. So if you did from -2 to 2, this one probably going to cancel out that one. Okay, or vice versa. So we keep them. So what goes between -2 and 0? Who's on top? F. So we put F first, which is, what is F? 3x cubed minus x squared minus 10x plus x squared, because it's minus g, plus x squared minus 2x dx. Okay? Let's go on and write the other one, plus the integral from 0 to 2 of
G is actually first, right?
Yep.
So it'll be -x squared
Minus x squared
plus 2x
plus 2x minus 3x cubed plus x squared plus 10x dx. Okay? Now, second?
We're adding the integrals, not subtracting them.
No, we're adding, yeah. Yeah, because the area would be this area plus this area. Okay. Otherwise, all for naught, and we'd be subtracting them away. Okay.
That's why we separate them.
That's what?
That's why we separate them.
Yeah, exactly. Okay. So let's combine terms. So my A is integral from -2 to 0 of 3x cubed. That's the only one there. These two add to 0. Look at that. And this gives us a minus 12x dx plus the integral of minus, add to 0 again. That looks like 12x minus 3x cubed dx. Don't think this is going to be too awfully hard to do the integrals. I will have to erase some space here to do them, I think, just to make it a little better. All right for me to erase up here? Okay. I hope y'all are okay with it because I'm doing it. Okay. I found that I've erased so much over the years with this computer, my screen has gotten a little scratchy. And that's a bad news. I hope it outlasts me, though. Okay. All right, so let's do our integration and see what we get. Integrate the first one. Antiderivative of 3x cubed. 3x to the fourth over 4 minus 6x squared plus
Negative 3x to the 4th.
okay, let's just do the first one. Why not? Otherwise I get confused.
6x squared.
6x squared
Minus 3x to the 4th.
that doesn't look too good. Oh, wait. Let's put our limits in here from -2 to 0, and this is from 0 to 2. Okay, don't just do them there without the limits. Otherwise, you just created 0. Okay. All right, so let's plug here. I'll do the 0 part. Okay, done. You do the -2 part. What does that give you? It's -2 cubed. I mean fourth. Okay, say that again. Okay. Well, the 16 up here, right? Okay. 4 in this. Okay. 4 will go in the 16. 4 times. So 4 times 3 is 12. Minus. Oh. But remember, this is all minus here, right? Because we've done the top one, and it's minus the bottom one. Okay, and what does this give us?
Also 12.
Really?
Wait, no.
Oh, okay. 24. Okay, but that was a minus 24, right? Okay, so this comes up a minus 12, but you got a minus sign in front, so that is a 12. Agreed? Okay. Plus, now when you do this one, plugging in a 2, you get 24 minus 12. And I'll do the 0 part. Okay, done. And what does that give us? Plus 12. And 12 plus 12 is 24. Very good. Let's see how. Oh, look at that. They got it too. Okay. Now they have a little remark here at the bottom half of page 447, and it says, in example 4, notice you obtain the incorrect result when you just integrate from -2 to 2 and do f minus g, because you wind up with 0. Because these were the same areas under the 2, but you subtracted the 1 and it came out 0. Okay. When the graph of function y is a boundary of a region, it's often convenient to use representative rectangles that are horizontal. That sentence almost makes no sense. Okay. When the graph of a function of y is the boundary of a region, often convenient to use rectangles that are horizontal, because if your functions are of y, then it's good to take your dy, because that's a good thing to do. So, when you have functions that are functions of x, then take the x's. Generally, that's going to be a lot better. So let's move on to example 5. And I don't think they show this one either, which is a real shame because it's a fairly new piece of information. But they chose not to, but we'll do it. Find the area of a region bounded by the graphs of x is equal to 3 minus y squared and x is equal to y plus 1. Okay. Now both of these functions are functions of y, not functions of x. So what would you do first? You've got several options. What would you choose to do first?
We need to find out which one's on top.
Okay. I think before I did that, I'd like to find my boundaries first, my points of intersection first. Let's do that first. And how would you do that?
We just want to set them equal to each other.
Say again?
We want to set them equal to each other.
Yes, exactly. So what would that be?
3 minus y squared equals y plus 1.
Okay, and what would that give us? What would you do next?
Put them all on the right side.
I like that. Okay, so let's add y squared to both sides. Okay, I can't write. Whoa, don't do that. Okay. Okay. And we'll also subtract 3 from both sides. Don't you see? The left-hand side becomes 0. Right-hand side becomes y squared plus y minus 2. And what might we do with that? Say again? What'd you say?
You said FOIL method.
Oh yeah, I call it unfoiling. Got it. I can't hear well. Plus 2 minus 1. I believe you're right, because the innards and outers, it'd be y squared, plus 2y minus y, that would be plus y minus 2. That works. So what does that make you y's? -2 or... Okay, so we're going from -2 to 1. Let's pick a value in between those two. 0, why not? So when y is equal to 0, x is equal to 3. And when y is equal to 0 here, x is equal to 1. So who's on top? The first one. Okay. So let's go from there and set up our integral. The area then would be, help me, integral from -2 to 1 of Yes, which is 3 minus y squared
minus y
minus y.
plus 1.
Okay, or you got parentheses in there or not?
No, it's y plus 1.
Okay, in parentheses?
Yeah.
Yes, okay, that's fine. I couldn't hear the parentheses, so, okay, dy. Because we're in, got functions of y, we make it a dy. Then this is y going from minus 2 to 1, so those are right. So what would this be? A is equal to integral from minus 2 to 1 of of 3 minus y squared minus y minus 1 dy, and I can simplify that a little bit more by integral from minus 2 to 1 of 3 minus x, no. That's what I was trying to integrate. When you subtract those, what do you get? 2 minus y squared minus y dy. Okay? All right. Why don't we take the antiderivative of that up here? That be a is equal to 2y
Minus y cubed over 3.
y cubed over 3 minus y squared over 2. Evaluate from minus 2 to 1. Okay, so your a is going to be, let's plug into 1, and what do you get? 2 minus 1/3 minus 1/2 minus, this time I think I'll take a little more care. I've been rushing through these. So let's plug in a 2 times negative 2 is negative 4 plus, I put a bracket there so we can just do with what we got. Plus, I did the plus, I gave 8/3, right? It's in parentheses, so it's minus, that is a 2 here, by the way. Minus a 4/2, right? Which is 2. Yay or nay? This may not have been a good one to do this on. Okay. I did the minus sign here because I'm using the lower limit. So in the bracket here, I'm plugging in the minus 2 in this bracket. So that's 2 times the minus 2 is minus 4. And negative 2 cubed is minus 8. And minus of minus 8 is plus 8/3. And negative 2 squared is positive 4. Minus 4 over 2 is minus 2. Now, let's see if we can manipulate with that. In here we have a 2. Let's wait on that. In here we have a minus 6 plus 8/3. Okay? But you got a minus in front of it, so that's going to be a 2 minus a minus 6 is 8, right? Minus 1/3 minus 8/3 again gives us minus 9/3, so that's a minus 3. And then you got a minus 1/2 left over. Okay? So that comes out 5 minus 1/2, which is 4.5 again, which was 9/2. Seems like we've been there before, doesn't it? And we have. And that gave you 9 halves. Does that make sense? Look, yes.
When we have 3 points of intersection, is it going to be?
Okay, a little louder.
When we have 3 intersections versus when we have 2 intersections.
Right.
I noticed like there was like a major difference. So one was we had to split them up because their areas were too similar. There would be like a 0 difference.
Okay.
But
on that case, it was the case, right?
Yeah.
Okay. However many points of intersections you have, if you have 2 point of intersection between these two, pick a point somewhere in between the two, find out who's on top. If you have 3 points of intersection, find who's on top here and who's on top there. It could be that this one went like this and this one went like that, so I don't know how that would have worked, but
no, you meant
yeah,
it's like
right. So the odds are it will be in opposite directions, but always between any 2 consecutive points of intersection, find out who's on top. I think just about always they're going to flip, but always verify.
Okay.
Yeah. And when you only have 2 points of intersection, pick 1 point and it's going to tell you who's in between. Okay. So we got 9 halves again. Okay. They show the graphs in the book and they're really worth looking at. It's just that sometimes I don't do a good job graphing. Okay. Now, they do show something else in the book, and I wish, because we don't have any time, I'm just going to hold it up here. People at home can't see this, so y'all are all here. We have perfect attendance. That's the advantage of perfect attendance. One of the many, okay? What we did was doing a dy and measuring from the right-hand one minus the left-hand one, and that's what we did. You could have done dx's, but then you have to split it into 2 pieces. Here you're going from the lower one, which is the quadratic, up to the higher one, so this minus this. But here you're going from the upper quadratic to the lower quadratic, so from the square root. What a pain in the neck that is to do, but you could do it, and if you did it that way, my hands won't hold it, you do get the same answer. But it's so much harder to do. So don't do it. I mean, do it the easy way. Now, some of you are new to my class. Others have been here before. I always say, to be a good mathematician, what do you need to be?
Lazy.
A little lazy, exactly. Always find the easiest way to do the problem. Don't do it the hard way, okay? Be lazy. Find the easy way as long as it's the right way, okay? Now, unfortunately, I'm afraid we're awfully close to running out of time, so we'll start the next time with integration as an accumulation process. However, we did get far enough along. Oh, came so close to finishing the section. Homework exercises here. Now, again, since we've got new people here, or a new person here, I assign odd number exercises. Why? 2 reasons. First, the answer to the odds are in the back of the book. So if you do the homework exercises, and you choose how many you want to do, I'll say any of the odds 5 through 9, okay? Those answers in the back, if you do 1 or more of those and you get the right answer, keep going, okay? You're fine. But if you don't get the right answer, you can't figure out how to get the right answer, then you can go to calcchat.com, that free website. You don't need a code or anything. Your grandmother could go to that website. She's not enrolled in the course, I don't think, and she can still see it, okay? And calcchat.com will show you how to work out that solution. But if you're still not certain about it, number 7, you can go to calcchat.com, because that's in a red text here. And let me also hold this up for you again. And every group of exercises that has this little QR code, is that what you call it? You can use your phone and click on that QR code. It'll take you straight to number 7 and show you how to do that. So your phone will do it for you that way. Okay? Then do either 11 or 13. They're both at CalcChat. 11's at CalcView. Do any of the odds 15 to 27. They're all at CalcChat. 17's at CalcView. Do 29. It's at CalcChat and CalcView. Do any of the odds 31 to 35. They're all at CalcChat. Any of the odds 37 to 41, they're all at Calc Chat. 37's at Calc View. Do either 43 or 45, they're both at Calc Chat. 47 or 49, they're both at Calc Chat. 51's at Calc Chat. Stop there, and we'll pick up there after we do accumulation. Good deal. Any questions? All right, we'll see you all on Wednesday, right? Another perfect attendance day. I can see it coming, right? Good deal. Okay. Any questions?